Hello and welcome to another episode of Reverse Engineering with Warranty Voider. Today on the menu, Solidworks and its file format. Well, sometimes I get asked to reverse engineer other stuffs and games, but the overall process is the same, so I just wanted to show this here. And where do I start? This is what I already got. I guess I start at where do I get these files from. So there's this catalog, for example, of different parts that you can have for your machines that you want to build. And for each part you can get the Solidworks or different formats as download. This Solidworks file format isn't documented anywhere. And so I was looking into figuring out how I could possibly still load stuff out of it and see how it's structured inside. So the first thing is, well, finding a program that can actually load it. So obviously this eDrawings program that is part of SolidWorks can load these files. Let me demonstrate that. Oh yeah, in the meantime it's doing stuff here. But let's talk about this later. So, okay, it loaded the whole thing, and obviously there must be code in here that is able to load everything. If I look into the file folder, there is a lot of DLLs here that could possibly load these files. So, the first thing you would usually do is just record file access. So I have different breakpoints here for different stuff. I think create file and read file are mostly used initially to load these files. Well, how do these files actually look like? Let's check that. So first let's remove everything here. We will have a look at this later. So just looking at these files, it's pretty much garbage in here. It looks like there is header and stuff in here, but it's not readable. It could be compressed, could be encrypted, who knows. There's a lot of spaces in here, which could mean that this is just obfuscated, because zeros usually end up as garbage, anything values. So yeah, this isn't really readable, usable in any way. To make the story a little bit shorter, I then obviously figured out who's loading these files, and long story short, they essentially have some encryption obfuscation over here, so before they can read anything of this file, they first have to find the header. And the header isn't at the start or at the end where you would just expect it, it's somewhere in the middle. So they have some scheme where you step multiple block sizes inside the file from the end and check if a specific header signature is detected, and then it starts the decrypting stuff. Okay, so this is the end of the research, right? No. Obviously something is done after this file is loaded and decrypted. Obviously it's taken apart more. So after a lot of research and looking between these files, I came to this DLL that does a lot of the loading. Let's see if I can quickly find my start point that I found for this. Yep, no, not the easy way. So, to search for strings that are not encoded as ASCII, like you have in your hex editor, where 1 byte is one character, you can have different encodings, 32-bit, 16-bit, or 8-bit, and you can let either just find all occurrences in all encodings of that. So let's do that. And I've been wrong. Okay. Let me find this thing here. Control B. This would be Unicode. Yeah, on the first search you cannot see the progress bar. On any consecutive search you would see a progress bar. So please wait a second. Come on. Oh, plenty of occurrences. Where is this? In document manager. Nope. That is not the one I'm looking for. References. So then, where are you? This looks better. SVDL reader. So it is in here. I know what are you doing here? All the items. Oh, it's 16-bit. Oh, and now it finds it. Well. Okay, let's see where this is used. So, lucky for me, a lot of stuff in here is named. Some that I named myself and some that is named by runtime type information. There's this little plugin if you have one of the average leaks, otherwise you can load this plugin as well. It's called Class Informer and it already finds a lot of class names for you. If you want to know why this is possible, please Google RTTY. Real-time traffic information. Nope. C++. Okay. Runtime type information. These in English for all the viewers. Alright, so stuff essentially so you can print class names and member names during runtime. And yeah. What's the different class employee? So this is reflection stuff that you would need to call or to find a class by name, for example. And so it obviously tells me a lot of stuff, of metadata about the reverse engineered stuff here. And you keep using stuff. So these define structures and their names and how they inherit from each other. So for example, let's take this class. This inherits from C dockside, C base pane, C window, C command target and C object. So if you would look this up in memory, you would see virtual meta tables for each of these classes. But let's not get too bogged down here. Essentially here we have a good example how this whole loading part works. First we get this manager and tell them open this file. Okay, if that worked, we tell him to get the file and we check if it's valid. We have functions in this DLL that can load the version, for example, but which is interesting to know which Solidworks version was used. It uses a lot of C strings in here, so this is all MFC standard. C string MFC. Do we have this in English too? How do I change my language? Sorry for the interruption. Can I change my language here? Nope. How useless. Okay, then do this by hand. C string. So this is another invention of Microsoft, to another way to store characters besides char, white char and the likes. It has a lot of helper functions, but let's not get too close into this. It's just keep in mind this is part of MFC as far as I know. Standard MFC. Paste application. Yeah, so yeah, C string are exported from MFC DLL. So yeah, that's what they're using internally. And they have a function that is called attach to node. So I think internally they have, after the file is encrypted, something like a tree structure. And imagine it like a file system. It's so attached to node would be like open folder, I would say, with the different names that is passed in. So here we create the string v13 and pass it in here, release the string afterwards, and everything was okay. Then we attach to the next node. Most of them start with contents and then some sub item. In my tool I already have a lot of these pre-written, pre-coded, because I already debugged this, of course, and just looked which keywords were used at all for this function, and so these are the most common combinations that I have found. And where is it? After a while, if this works, for example for OLE items, then it finally gets an archive from this. And this is of type C archive. Now this is another MFC invention. Okay, so how does this work? If you have some binary, have I already unpacked one of these? Yeah, let's unpack one of these. So, okay, one by one. We get this archive, and from this we load stuff. Not quite sure if these are correct, because I have created these structures. But essentially it's loading, oh yeah, it's loading a COLE document. Not quite sure where the actual call is right now. But yeah, then we close the archive again and everything is fine. So these archives are just byte blobs, so I was like, well, I could just print them all out. So what did I do in my little program here? I defined some function definitions. So these are just function pointers, and I define what types they are, what parameters they get, what calling convention, and what they return. Then I actually allocate pointers for these functions, which I later fill out so I can just call them. And essentially this is what I do here. I just load the DLL, and the pointer is just some offset inside the DLL. If you want to know how to quickly get these, for any function here, let's take this one. You see the address here is, this is 180 million hex plus some offset. We can go to the very start of this. Besides the header at 1000 hex, this DLL was loaded to 1800 million. Yeah, 1800 million. So whatever address you have here, you can just ignore the upper part and take the lower part, because usually it doesn't get over 10 million. And this is your offset that you can use in here and say, yeah, this is now loaded in memory, the whole DLL, and now this address plus some offset is the function I want to call. or is a pointer to it here in this case. So and I do the same thing. I get this manager, I open the file and load the version, and then I try to extract all of these streams, all of these archives that we just seen, to files. And that's what's happening if I drop it here. I already did it. So let's just redo it. If I drop it on my tool, all of these files are generated, and as you see, they are the combination of these possible folder names, I would say. And they have some data in them that is now actually readable. So this is a valid string, this is valid text, stuff like this. So from here I would like to know how to further take these apart, which is the actual format, I would say. And for that we have to go back to the archive. So what we get out here is a C archive, and the idea is that when you have binary data, like let's say this here, you want to serialize data in and out of it, and that could be of different types. The basic atomic types obviously are bytes, anything ASCII, and 16 32-bit numbers. Strings and byte arrays essentially are saved with a length code and then the actual data. And you just want to write code to say I want to read 4 bytes for this number, then 2 bytes, another 2 bytes, another 2 bytes, which tell me how much more to read. And so you want to have a way to write in code how to save this. The idea would be, let me write some pseudocode here. And just do this. Yeah, who cares? So I make a new archive, so some byte memory or... Oh, that's... Oh, it can only come from another one or from a file pointer. Okay, let's assume we just have a file, it doesn't matter. So let's define some variables we would want to save. Would be byte A. Alright, yeah. Do we have byte here? I think in Windows we have to write it like this. Byte, word. And later we just want to write something like this. Now, what happens here, I know this is not liking this. It's overloading these operators to do operation with the second parameter of the operation, and then be able to stream this into one line. Essentially what here happens, it first writes a byte, then writes a word, then it writes a double word. And if this archive would be loading, it would instead load or read a byte, then 2 bytes, then 4 bytes. In this way you only write one line of code, and then can already define a structure on how to serialize some data to file, to memory, network, whatever. So for this archive class, there are different functions to read and write stuff. Read a string, read raw bytes, and read class. Read class is an interesting one because essentially it takes the class runtime type information that we talked initially about. Let me show them again. All of these information here, and already knows from the runtime type information how the structure would be in binary, and just automatically loads all the necessary components like member function, member parameters and structures that have also the inner data to fill. Okay, so, well, how about watching these calls to see how one of these files is read? So I made some breakpoints. There's a few read functions in here that I've already found. Read. Let me quickly refine these. So, okay. Okay, they are called operator. Alright. Alright, there you have your operators. So, loading. So these would be the writing ones, and these would be the reading ones. So, if it goes to the left... No, wait, other way around. If it goes to the left, it goes into the archive, so it's writing. And if it goes to the right, it's reading from the archive, it's reading. So, and again, for all of these functions, I can find the relative offset to my DLL. I'm in the SWDL reader DLL. Actually, but I haven't found a good way to do this in here. So another good way I usually use is just taking a bunch of bytes. So this is the same address as we've just seen. So you have your 66, 89, blah blah blah. And 66, 89, blah blah blah. Let's check a few of these opcode bytes, copy them, and just find them in memory. Go. As you see, it's the second one, it's faster with searching for whatever reason. And here's one of these functions. Which one is it actually? This is a writing operator. Ah, that's why I don't have a breakpoint here. Let's see if you're at least at the right address. CE30, that is fine. As you see, the rest of the address is just some offset because every DL could be loaded at any offset. We have a move word, we have a move RCX, sub 28. Yeah, that looks pretty good. Okay, fine. So that's how I refine functions between here and there. Let's say I want to refine this function in IDA. I could just go here and copy RVA. That's a relative virtual offset. Relative virtual address, sorry. And if I go to IDA, go to just the RVA doesn't help us. We need the actual loading address, but we know it in IDA it's always 180 million, and we just have to fill up the zeros, and yeah, that's our address here. That match. So you can go back and forth between them. Let's see, and I already prepared that. So read byte array, read object, blah, 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 blah. Let's have a look at these breakpoints. Let's take read byte. Okay. At this address, the byte was already read. It's in AL and will be written at the address in that was passed to the function. Let's watch that in IDA. Where we actually add. Ah shit. Sorry. Copy RVA. A2 is where the operator, the second operator is passed in, and in this case it's reading from it, so it's written to it, and as this is just a pointer, we write to that address. So that's why there are brackets around RCX. RCX holds a pointer, and wherever that's pointing at, that is where we're writing. That's why the brackets are around. Anyway, at this point I can make also... At this point I can also see that my stack pointer before the return is adjusted by 28 bytes hex, and so I could actually, if I did this, have access to a lot more information, like the return value. This would be... Oh, we're not there actually currently. Can I make... I could just make it break. How about that? So the first part is if this breakpoint should stop or not. And the one down here is just if it should lock something or not. And in this case I just want to stop it so I can show what I mean. Close this again. So now we are here. We can see the return address would be something with 43500. And we want to access this. So first off we want to know where the stack pointer essentially let us return. So that would be the stack pointer plus the 28 offsets that we saw here at the end. By the way, this is for local variables to make space on the stack. So mod name is... Let me copy all of this out and explain each part of it. This makes more sense. Okay, this is just text that we print. Then we have some what's called expression, and then expression, more text, expression, more text, expression. So this expression tells me, because this returns me an address. First off, because I take the stack pointer plus the offset and give me whatever it's there. That's the address we want to return to. If we look at it, that is some offset somewhere in memory that's inside the DLL that is loaded at some address in memory. But first off, I would like to know which module that is, so which DLL I'm in. And now I want to have this RVA again, so I know the relative offset inside that DLL, which is way more useful than some absolute address where I don't know where the DLL was loaded. And then actually print out what value was read there. So let's step over this and see if it happens. So let's clear the lock, step over it. Ah shit, it was already printed out. Okay, let's wait until it was called again. Okay, and here it is. So when it stops, it already locks everything. It was called from this DLL and this offset. Let's see where that is. So. So this obviously uses these operators to read stuff. This is a byte. Not quite sure what this does. These all load different structures at once. Seems like these are just vectors. This is creating a new vector. And then it's filling it from here. For example. Okay. And here was my byte call, I guess. Because this is where we return to. Alright. So, and if it was 1, I guess. So, what was it? It was 0. So we won't get to the other calls. Okay. Somewhere in the middle of reading this file. Which file we don't even know yet, but one by one. So let's just continue here. Doing more logs, more entries, and as you can see, it did a lot of reading here. So drawing. So let's have a look at this more closely. By the way, that's also the reason why it always takes so long to load, because of my logging code. Okay, that's all of it. Let's copy it. So, here's another thing. We still have the attach to node call, which tells me what was opened and then read. In this case, I know it's content and then all E items. Do we have this here? Okay, it's one big file. So let's see. Only items. It reads one D word, that is one. That is already correct. But then we want it. I'm sorry. Then we want a doc item. But instead it reads this. It's a length of 9. And then it just reads a big byte array. Okay, let's see where we end up. In the middle of somewhere. But yeah, this could be true because I think this is a preview bitmap or something like that. Preset, brush. It's a lot of stuff. And the next word that we read is 5500. Is it even part of this file? Somewhere in the middle. Oh yeah, that actually appears multiple times. Okay, never mind, so let's go back. Still skeptical that this is correct. I'm still thinking I'm missing some read calls, breakpoints. And then yeah, something like this is missing. Okay, but never mind about this. Let's say we are at this point. So next is a double. Does it mean 8 bytes? And double 1557. Oh, look at this. So these values match. (0025). Okay. And -7. Okay, so we can observe it reading this file, but it seems that I'm still missing data or reading calls. Okay, let me drink something, just a second. Okay, I'm back. I hope I sound better now. So something has to have happened between reading these 9 bytes, which I'm pretty sure come from here. Also, I don't see where it consumes these 9 bytes. The 2 bytes with the value 9 in it to read that. So let's figure out where this was called from to read at least these bytes. That would be byte array, that makes sense. With this offset. This is actually not the structure I wanted to reverse today, but this is a start. Okay, let's figure out the exact point. So it's really this call that we return from. This must be the very last thing. I should reverse engineer the structure of this archive. What the hell? It's just fancy jump table stuff. Don't get too confused about this. Huh. Here we access the VMT and call something from it. Huh. So I'm missing calls here. And the next thing that happens would be reading this big blob. By the way, is this value somewhere used in here? Huh. How about here? So we're missing a few reads in between. How is that possible? Well, let's see who's reading this. It's all archive stuff here. Okay, so let's figure some things out here. Obviously there are calls to the archive here that could read or write something or do whatever, so we have to find out what actually gets called here. So the first thing is to let IDA guess a structure for the archive itself. Then we see these are VMT pointers. And I would like to know what it's pointing at, to know what methods there are. Then we can replace this pointer with the structures of the actual functions. So how sure are we that any of these are called? Random chance? Well, let's try random chance. So this line of code is essentially decoded into that. So 112, what is 112 in hex? 70, okay. So at this point RAX holds VMT pointer. Actually its target. At this point RCX holds well, let's take breakpoint here, you will see. So where are we in hex? See if I can find it that simple. Okay, there we are. Let's make a breakpoint. And let's see what happens there. So RCX is supposed to point to an object, okay? This is the pointer, VMT pointer. See where it points at. To a table full of functions. Great. And please give me the RVA. You can look it up here. Stream file. Get position, read, write. Okay. Let's make this into a VMT struct. Okay, these are all the entries. And these will be... This is 64-bit, so 2-word pointers, quad word. So the question is, how do I sanitize? Didn't I have made a tool for this? Let me quickly check. I don't have it here. Okay, then do it by hand. Never mind. I think this is crashed. Okay, never mind. So. I'm not quite sure what's all allowed in function names, but we will see. File title, the long ass name. You will see what Ida doesn't like. Actually, these names are a lot better than what I had before. I mean, I can keep these ones because they are kind of useless. I have something like this. Just giving it names that make sense to me. You will see in a minute why I made this. And now I made a tool to automate this for me, but I can't find it right now, so please bear with me. So we don't have duplicates. Okay. EMD stream file. Okay. Now let's tell Ida about it. Simply accepted it. Okay. So let's go back to our archive. And make it such a pointer. Now we should see not quite what I expected. Oh, I don't care, here I get another pointer star. Okay. Read this weird function. Read. Okay, so this makes a lot more sense. So only thing I would like to do now is to import this type into the actual type. I'm not sure if it's bigger or if I'm missing stuff in the gap here, I'm pretty sure. So, because this was found but not declared in structure. So, struct. Archive. So now I should see this everywhere where C archive is used. Let's go back. You've been here before, looks like. Just for fun. I would say this is then a data pointer. Yeah, and increases it by 8. Makes sense. Okay, and now we find out more. Okay. Let's go back to our interesting parts. Somewhere in between here we miss readings. Let's see if we can now find out more about it. Turn from here we have the archive, here we have different reads. It's different sizes. Also, what is this function doing? Nothing. Okay. That's kinda... or it gets overridden. That is possible. But yeah, I think it's not implemented here. Instead, what I would like to know is where this read function is going to. Read. No went. So let's find this in memory. Okay. Let's see how that works now. Oh, we still have the other breakpoint. Okay, let's deactivate this for now. That's the one I meant. And yeah, let it run, do its stuff. And now activate it. Okay, we got here. What does IDA tell us about the parameters? I assume A3 is count and it's saved on R8. Oh, so we read 10,000. Okay. And where do we read it to? RDX. See if that's true. Not quite. It's not 10,000. Oh no, that's just the data matches. Rect item. Okay. By our log we are where? Older items. Okay. Read a big block of it. Oh, I think it's just loading it one by one. Okay. Good. Let's make this a smart breakpoint again. Let's copy from here. So we want this to not stop, but to lock. Stream read called from. At this point, nothing to the stack was done, so the returning address is directly where the stack pointer is pointing at. So no offset here. And size R8. Okay, and let's let it run its course. So you can see it's overwriting the same memory a few times. Okay, and now everything together. So what have we now? Stream read. So we definitely got this read. Then we would expect doc item. This is just the class that the object that wants to deserialize is named. Then we reach the byte array of 9. Pretty sure it can only be this. Somehow we get to here. We skip 18 bytes. Okay, and then from here we read the big block. And then continue with yeah, so stream read is just when it continues buffering. Interesting. Then this is the next value. We got this one. Okay, that all works. What I don't get is how it skips the start here. But we also, as if I remember right, had a function to seek. Get position, get length, set length, seek. Okay, where you at? So maybe it just seeks in between. We are looking for hex. Oh, right below it. Great. So we can see that more. Seek is used. Let's find out more about the function. Seek. A2 is on REX and R8. Okay. Nope. R8 and REX is both 0. This is probably seeking to the start. Okay, let's copy from here. So mode would be seeking from start, current or end position. Okay, everything together please. Actually, let's copy this. Notepad is just faster. Stream seek. Ah. Is this ever used with other values? Huh. Did I do this wrong? X, right. Okay, but at least the mode makes sense. This is negative, I don't know. Oh, negative from the end. Yeah, okay, never mind. That's not helping. So let's go back to where this was red then. After the D word, for example. This would be this data here. As far as I think, this is just a count. How many objects are in here. For example, if I open this one, there are multiple. And this is another class that's get deserialized here. But okay, I want to know more about the start of it. Okay, so let's say this was a count. Yeah, and so often it tries to read an object from a specific RTTY. Okay. Nope. Nope. This is the archive. And yeah, then we read object with this class. Let's call it the doc item. And this has, I think, only this creation function and this subclass. Yep, this is a constructor. This creates a new instance of this. And yeah, this is a inherited class, command target. Okay, this is just to create one of these. How is this serializing working here? How do I get back? Why, and also, why is the archive needed? Ah yeah. Create object. Check count. Ah, was about to say, didn't we already updated this archive structure? Map object. Interesting. A little complicated. I don't want to understand how they actually implemented the handling of these runtime class definitions. I just want to make use of it. So I can get these read. So doc item is already right. Okay. Someone read this. At this point we already read various things. So I want to go back and see where could I have possibly skipped something. So this is an archive. Look at this. So here we play around with the data pointer. Okay. Then we get the length. So just looking at this data pointer, here we take the len out. The length. I don't know how to pronounce this. Which would be, let's go back to this, the thing I wondered about. Also probably I have to, oh yeah, this has a few references. Okay. This function essentially reads so and so many bytes and stores this in this string. And make sure the end of it is 0. The name is not allowed to be longer than 64 bytes. Okay, that makes sense. And so this part here, oh actually, also why is data pointer? It's void. Okay, maybe I should show the casts here. Okay, taking this as a 16-bit pointer, it's increasing this by 1, so 2 bytes. And so we have this past here. So what else is with data pointer happening? A1 is an archive. Okay, this throws an exception, so I'm just assuming this means loading. And type bool. So is this a loading function? If you're not loading, bad. Okay, that makes sense. So this is probably the size. Let's call it data end. So this is what left of it. Possibly a lot of stuff is happening here. Okay. Actually, wrong place. So let's for a second ignore what happens right before it. If data pointer bigger than data end. Not quite sure how they use these data pointers here. Let's assume these are checks. This is a check. It's another loading check. This is another check if you have enough data. This is another read of 2 bytes. So essentially what I'm missing is Did it read these 2 bytes or these 2 bytes? And where's the rest in between? This function is called twice. I assume this is data buffer in. Meaning if we have more data to load, it just looks to load more. So I'm still... So we read something from here. Data pointer plus 1. So I would assume then that it's just reading this here, and we still don't know who's reading that. The problem with these access to data is that you cannot make a breakpoint essentially there by a function that's reading 2 bytes. It's just doing stuff with pointer directly. This could come from optimization or be just done by them. Oh, here we check it. You are in archive. So this must happen right before V8. Here we read it. Okay, so we check if it's 7 FFF. Else. What the hell is this? I assume this is some weird bit mapping. 7FF. Here we have the upper one. It's derived from. Interesting, so it means either it can be this value or this value. So I guess this is nested and this is not. And what do we have? Not. Okay, we need to read this, okay. Then we have the string. Let's go back. Then we load the class, or probably creator for it, from this name. Which in our case would be C-rect item. Okay. So we have that part. Then we skip a lot of stuff, especially this here. And then we read so much. By the way, by the end of the video I do not want to have the full format explained or reverse engineered, just showing how to get piece by piece ahead. That's our function here. Whoa. A lot of archive action here. How did we get here? So allocation. Oh yeah, wait. Up until here, this is essentially, let's say, runtime header. So I guess this is nested or not. I don't know. Linked name and sexual name, so it can load it. And this is probably now a function from that initializer. Read item compounds. Really have to look into older streams. Okay, now I'm lost. And we are back. So at this point, our archive is here. So data pointer. Plus V8. So we skip data here. Alright, this is at the end now, because V8 is what's remaining. Or this could be reduced to V3, whatever that was. So we should see a read here. Oh, stream read. But that came after our call. Wait. So it must be something called at the very end here? Not quite sure. How did that happen? Huh. This is doing nothing. Very confusing. Another confusing function again. I'm still thinking this is just updating the buffer to read more. This is a lot. Pretty sure I'm missing a function somewhere in between here. Was linked. Use read again. Oh, maybe this just reads more. So still reading the header. Okay, never mind. So this is reading. What? So it must be called inside here. Okay, it's getting pretty late now. Let me make a quick guess of what I just see here. Well, this definitely is the buffer size. Question is where this was cut out from, but I guess somewhere in here. It's an actual buffer of, I don't know, bitmap data, who knows. Let's work this, and then yeah, we already have, we should see decimal values, possibly just dimensions and counts. The thing is, there's a lot of stuff in here. As you can see, there's a lot of reading involved. These are usually done in loops, so I just wanted to find the inner loops. But yeah, I didn't get so far. I saw some of these, but not in a preview example now. Anyway, so the inner structure would be quite some time to reverse engineer, but you can help yourself with logs in between. Not every read is essentially a call to a function. A lot of reads in between are just code somewhere in a function. So finding those will be a lot harder, but I can make breakpoints on when this data pointer changes, which would be a lot with all the checks, but logging it out, you could see every place in code where this data pointer was accessed. Yeah, I will probably show this in another episode. Anyway, thank you for watching, and hopefully this is showing a little bit of the tricks you can use to reverse engineer stuff, and how you can use you can bypass encryption if you have some codes that can already do that and call this directly on your own. So yeah, I hope this was interesting and you learned something. See you next time, and have a nice evening or day. Bye.